So welcome back to our diffusion sensing theory. So today is going to be part 4, and I'm going to discuss diffusion and triangulation sensing, recovering a point source in dimension 3. So quickly, in the previous YouTube, I explained flux coordinate, what happened in dimension 2, and basically the role of these sequences is to find out a theory that could explain how neurons or any cells can navigate in a tissue such as the brain. So let me remind you the biological concept before we move to the mathematics. So this is an example of a neuron. You have here a growth cone. It is on the dish. At time 0, there is expression of gradient concentration of a transcription factor. And what you see after some times is that the growth cone is going to grow. If I show you how it would work, the growth cone will move, and after some times, this is what you would get. That is, it creates, let me change color, it would create here this curvature, and you have the growth cone moving toward the target. And basically, when you have morphogenes gradients, they guide the development of axon over large distances. This is here an example, which I have already shown previously, where you have the neurons and the growth cone that move along different fields here of expression of different morphogene until they can target or move to their final destination, although there may be here some uncertainty, and there are more into the biology that will be involved in the final target, such as pruning, where neurons can lose some of their connections. Okay, that's the context, the biological context. And so what we have developed is synthetic motion navigation. So we have here the position at time 0 of a particle, which would be the growth cone. And here you would have a source, and basically the cell, as it moves, sense the local concentration, and this will be explained in further publications. I just want to illustrate the purpose of the YouTube of today, and that after some times it moves toward the target, as we implemented here through these simulations. So diffusive fluxes through narrow windows. So what are we interested in? We are interested in the distribution of, first of all, particles that would be emitted at a source. So this is the source location, and each particle moves independently, so the concentration satisfies the classical diffusion equation, dp dt equals d Laplacian p, where d is the diffusion coefficient. And this is the cell that will sense the motion of particles. So the cell is going to be reflective, except, for example, here at 2 locations called 1 and 2, where you have absorbing windows that models receptors. So upon touching these receptors, this area, each time it does so, the receptor is absorbed, and you count it at +1, right? So this is basically how this receptor counts the number of particles by experiencing the flux. So we have here absorbing boundary conditions, while we have reflecting boundary condition. At any other places, if we have a particle moving, it is reflected. So we can determine the probability, Pi, that a particle hit and is absorbed at window I, and for this we can use the Green's function, which is solution of minus d Laplacian P0 equals the delta Dirac. So this is the Green's function. And here, in addition, it's not exactly going to be the proper Green's function because we have a mixed boundary value problem. So for this, we need to use actually the original Green's function, which satisfies this condition with dj0 dn equals 0 everywhere on the surface. So we have a pure Neumann condition. And what we do is we subtract. We take the difference P0 minus G0 here. So P0 comes from here, G0 comes from here. And we have W. And W satisfies this classical Laplace equation with mixed boundary value problem. And so we would like to solve this equation. And in particular, as we are interested in, can we, from the flux, I will explain this later in the next slide, can we, if we know the fluxes, that is, if I know T dp0 dn at each hole, let's say 1 and 2, or more if they are, can I reconstruct the position x0 of the source? So for this, we can, so I have explained already how to do it. I can explain the solution. This is a previous YouTube, how you can expand, or you can have an expression for w of x with respect to the Green's function. And for this, you have to use Green's identity, which I'm not recalling here. I will refer to a different YouTube for the Green's identity. And so basically, this allows to write w with respect to the Green's function and the fluxes at each window. And we know the flux. This is known, this is the well-known solution. You can look at the book of Cronk of 1975, Cronk books about diffusion. And you know that it is expressed as a constant divided by epsilon square minus r square square root, where you have a whole of radius epsilon centered here at position xi, right? So if I go and look at what happened at each center, so w of xi, right? So by definition, it is equal to minus j because p equals 0, as we have seen, and I call this alpha k. So if I write this equation, this ensemble, these sums at each of the holes, I have, for example, here w kq equals this is the left hand side, and the right hand side is going to be the sum, which is written here, where you use here the expression of the flux, and here what you use is you have to calculate, so this is a term for k equals q, right? And here the 2 pi here, I think it comes from it comes from the expression of the integral of this quantity when you calculate over the area. And so you obtain a system of 1, 2, and n equations that you can summarize on the form of a matrix of the type alpha are the unknown, A are the coefficients that are unknown, and so you would like to invert this matrix equation where m can be written as a form of a diagonal term plus another term which is expressed here where everything is off diagonal. Delta is theta epsilon multiplied by identity, where theta is given by this expression. This is just the result of the calculation where b is a constant. B is a constant, and a here is, for example, if we have a ball of radius r, this is the radius of the ball, right? Of radius r. And so you can invert. This is the inversion. So you have to invert formally. You can use this as express it as the sum of this infinite contribution. And we assume that the flux here is known. You know how many particles per unit of time arrive at steady state. So you can use now the fact that this flux can be expressed as a function of A of k, and A of k as a solution of this matrix. And you see that it depends on this alpha k that depends on x0. So here is the problem. Given the ensemble of flux, for example, if you have 1, 2, 3, or more receptors, can you find the position of the source x0? This is what we have called triangulation sensing. That is, can you triangulate the position of the source if you know the fluxes at each of the small hole for the cells? The problem that we have initiated in 2017 in dimension 2 and 2020. We have first publications expressing formulating this problem and giving the solution, and I'm going to continue towards what we have found. So how to find x0? So I have already done a YouTube to explain what happened in dimension 3, where the solution can be expressed as a sum of 3 terms. So you invert the matrix. I'm not going to redo it. I urge you to have a look at this YouTube. So you get the expression of this coefficient A, A1, A2, A3. With respect to this distance between the narrow windows, there is here the expression of the determinant. And the fluxes here are known. And so if you want to invert this, as I've shown previously, suppose you ignore this term, then you have to look at the intersection from here of 3 spheres. And the intersection of 3 spheres has at most one solution, and the solution is exactly the point x0. All right, so I refer to this previous publication for the dimension 2 and those 2 ones for dimension 3. Right? And so we have called in the past that phi1, phi2, and phi3 would be new form of coordinates which we have called fluxes coordinates. Right? Those are called flux coordinates. Because with this information of this coordinate, you transform and go back to initial Cartesian coordinate for the position. So now I'm going to show you in the general case for a ball. So this is the case of the plane. So how do you compare analytical result with simulations? We design an algorithm to say we don't need to simulate everything. You start at a position here x0. You map the position here to a disk of a given radius. And then you start your Brownian simulation inside a disk. You run a simulation until it hits a target or escape. And then you return in dimension 3 with a certain probability, which is r, which is the radius of this disk, divided by x0, which is less than 1. So with a certain fraction, the particle is lost because it represents when the particle goes to infinity. And we know that can happen in dimension 3. And then we can compute the statistic, for example, of splitting. How many particles goes to 1 before to 2? What are the difference of fluxes depending on the position? So for example, here we vary the angle theta, which is given here, and we look at the fluxes and the splitting probability, and you can see what happens if you change the lengths, if you change also the angle phi here for the position of the source. You can see that we have a very good agreement between the simulations, this simulation, and the theory. The theory is the continuous line, and the cross is part of the simulation. So another interesting example is now we have 3 windows, and from these 3 windows we can again calculate the total flux for various type of a triangle, equilateral triangle, a scalene triangle. We vary the distance to the source. And again, you can see here for different distances that we have a very good agreement between the simulation and the theory. And this is here the splitting probability, so that the sum is equal to 1. And we see for each of the window, which correspond here to the different colors, how the splitting probability changes. And very briefly, we can define a minimization procedure to look at a zero. So I will explain this toward the last slide, that we can, for these three windows, we can construct, this is in black here, we can construct the intersection of two of the spheres that I've described previously. And finally, the last point corresponds to the position of the source. Now I will continue to explain what happens when we can add some uncertainty. Like, suppose the flux is not known specifically, but we can add, let's say, a Gaussian noise of a given variance, let's say sigma of mean zero. And so, of course, in that case, the fluxes are random variable, and yet you are interested in reconstructing the position of the flux, but now there's going to be some possible uncertainty, variation. And so one way to estimate the error we are making, let's make this Taylor expansion to order 1. So this is this Taylor expansion that we have. And so x0 is the position. And then we have here the element of uncertainty, which are given basically by this Jacobian matrix that we have here. And we can define the volume of uncertainty given a perturbation eta, where eta is, for example, the amplitude here. It's going to be given by this formula where the determinant is a determinant of the Jacobian matrix. So basically we have to look at the eigenvectors, and if we have 3 eigenvectors, we can take the parallelogram constructed on this eigenvector A1, U1, U2, U3, and the determinant is giving precisely this volume. And we call this volume this uncertainty volume. And so what you are seeing here is the position of the source reconstructed, and I suppose you have some uncertainty, and so we have here 4 windows. And so if you have 4 windows, you can construct specifically 4 of these parallelogram. And so what we are saying is that if the cell has the possibility to combine and to do the intersection, then you see that the intersected volume is much less than any of these 1, 2, 3, and 4 separately. So this is the intersection, and the idea is that intersection, and then the idea is that the cell can be more specific into the reconstruction of the source using this red volume. So now another possibility is to look at how, when you increase the number of windows here from 3 to 9, how this volume of uncertainty is decreasing. So this is still an open question in terms of the analytical formula. But what we found here, this is in the log scale, that the decrease, whether the windows are located uniformly on a cluster or forming a group of cluster, it decays basically exponential, more than exponential. So we should have, in principle, a possibility when you add the number of windows to be much more accurate into this reconstruction if there is a possibility to combine the information of these different volumes. So this is another example in the case of a plan. You have here the different windows located at different position. In black you have the case of a volume reconstructed with a selection of these 1, 2, and 3 windows. And here is the case where you have 4 windows. And here you have all of them, and you see how you restrict the volume of this uncertainty volume. And this is here how you have this with a function of the number of windows. So another example is how important is the position of the different windows. And so here you have 2 examples where you have this distribution 1, 2, and 3 compared to the case where you have equilateral triangle. And then what we did is we varied the position of the source, and depending where the source is, you can see that the volume of uncertainty has very different behavior. This is these different colors in here, where you see that the volume is very nonlinear depending on the position, and this is expressed here in this curve depending on the angle beta here between 1 and 3. So to continue with this estimating the localization error, let's continue with this Taylor expansion. And now let's assume that we have this estimator for the position of the source, and suppose we know exactly where the source is. And so xn minus x0 is given here by the first order term of Jacobian, where we choose a triplet of 3 windows. And so when we now average of many realization, we obtain this formula. So we have any choice R of a window, so we have to sum over n. N is the choice of the triplets, and Q is the sum of a realization. So now if we calculate this expectation, we see that it depends on the amplitude of the noise. N is the number of total combination of windows. And then we have this quantity here, the traces of the product of the Jacobian, which is given basically by the sum of the eigenvalues. And this term here, when n is large, is bounded. So this said that the error that we are making decay like 1 over square root of n. There is also other possibility to define your estimator. You can give a weight and, for example, calculate with respect to give the weight which depends on this volume of uncertainty. And now what is very interesting is that what is the error of the source reconstruction with now this different analysis, where we assume that each reconstruction is a random variable. So you have the random location here, and you see that we studied 3 cases. The case where it is uniform, the windows are uniformly distributed. They are located here at the North Pole, and here they are clustered uniformly distribution in cluster. And so when you see this, again, you can see how this localization changes the distribution of the sources. And so we did this for different angles. So you can see what happened when we have pi over 4, pi over 2, and so on. And so this shows how spread in here can be the localization of the source. So another example where we have studied other parameter. So for example, we ask, given the distance L to the source, if we look at the radius where 99% of the points are following a radius center at x0, we look at how this radius increases with or changes with this distance L for this different configuration. And you see this is more or less the same, no much changes. Interestingly, when we look at the number of window and we normalize this radius by square root of n, we see that basically it converges to a constant, suggesting that we obtain for n large that this R99 behave like 1 over square root of n, the number of window, as predicted by the theory. So let me skip this. Another interesting quantity is the sensitivity. That is how far a cell can sense. And for this, we had to define this quantity, which is the difference between the probability at 2 windows normalized by the sum. And if we have 3 windows, we took the maximum of the difference of the fluxes. And since this difference behaves basically like 1 over x0 squared, where x0 is the distance to the source, as represented here, where we compared the theory versus the analytical formula. And so this gives us some idea of how far this a source can be sensed by a cell. And here you have example of if you have a detection at 1%, at 0.1% or 0.01%. So with such a small possibility to detect the difference between two, this is a threshold to detect the difference between two windows. You see that you can get basically maximum to 20 times the size of the cell, which is not much. Okay, so this is the same question, and you can see here the distribution, the various distribution for the different threshold. So here again we have looked at this is an XY plane, and you can see what happened in the Z plane. All right, and so I wanted to finish by this. So how do we reconstruct the location of the source here? So what we did is we wanted to look at the solution of this equation, which is basically telling that the flux, this gives us the flux information. This equation we derived previously with respect to x0. And so we have to do it for these three windows. And basically what we have to do is to minimize this, or to look at the zero of this for all of this. When you choose K, L, and M, this is the label of the window. We search for the joint root of this. So basically we have to trace the root contour in the plane until we find the intersection with the root contour. So this is what it is explained here. That's how we basically find this contour until we look at the zero of the other one. And so this is how we find the first zero, and by an iteration we find the third intersection, which is the position of the source. So to summarize, I've shown that match asymptotics yield analytical expression for the flux, receptor flux for a Brownian source. We use hybrid simulation method to avoid excess work for large excursion and avoiding to simulate a lot of particles. We said that the direction sensing, we can at least sense 5 to 20 size radius in a free space. This is something that we'll have to come back to explain how a cell can navigate much longer distance. We need at least 3 receptors to infer the source position with inhomogeneous accuracy. We saw that multiple receptors could increase the sensitivity by reducing the radius of uncertainty. So in the future, I'll show you what happens when we are at in non-stationary, when we don't have necessarily steady state of distribution, and how we can use combinatorics or morphogenes to have a more accurate sensing. All right, thanks for watching.